welcome to the concluding part of solar energy. So, previously, if you recall, that we had discussion about the introduction to solar energy, which we discussed about the parabolic collectors (PTC). We got the anatomy of linear Fresnel reflector (LFR). In this particular lecture, we will discuss about the concept of central solar tower, which are more common nowadays, and solar dish system, and we will introduce the concept of heat transfer fluids. Now let us talk about the central tower technology. Now central tower technology is quite simple, especially when we compared with the PST. They are well suited for large scale grid connected power plants and having larger economic benefits. Now it consists of large flat mirrors like this. Here you are having these large flat mirrors connected with the heliostats. Now these mirrors, they are focusing the light radiation towards the receiver. This is a central receiver mounted at the top of a tower. Now these sun tracking mirrors, these can be in a huge number, counting from say 100 to 1000. They are termed as heliostats. Now these heliostats, they can concentrate a large amount of energy, producing a high temperature ranging from say 500 degrees Celsius to 1500 degrees Celsius and sometimes even more. Now this energy we can utilize to heat high temperature fluids like molten salts or directly water to produce supersaturated steam. Now this the electricity generation principle after this step is same as we have already discussed, that you produce the superheated steam, then this steam is passed through the steam turbine generators to produce the electricity. The receiver contains a wall of pipes where the concentrated sunlight is used to heat the molten salt, sometimes nitrate salts, to a higher temperature like 550 degrees Celsius or sometimes more. Now this heated salt is then circulated to a thermal storage tank which is having high thermal efficiency, and the colder salt get transferred to the receiver from the cold salt storage system. Now the energy is then used to produce steam, which then convert this thermal energy to the electrical energy, and we have studied this various cycles, and the foremost cycle in this particular aspect is the Rankine cycle. Now at night and at cloudy days, when the heating process stops, the molten salt were stopped to pump through. To avoid the solidification of salt, electrical resistance element they may submerged in the tank, and a pipe tracing system with associated accessories is installed. Now question arises that what is the reason of solidification? So the solidification of salt can occur due to the melting point limitation. So as molten salt, for example, let us take the example of nitrate salt, they are having the melting point nearly about 350 degrees Celsius. Hence when the temperature decreases, it starts solidifying. Now this can cause the choking of pipelines on thermal storage, and it may create the further complication. So therefore this solidification phenomena is extremely important. Now the central tower system, this allows the storage of thermal energy, which enhances its use to supply electricity in various power grids, distribution networks, etc., when and where required, in night or maybe in a cloudy weather too. Now, as the technology runs on higher temperature, the efficiency of these systems are much higher than the parabolic true system. Now, advantageously, this system sometimes requires a flat land and can be used in some sort of a hilly regions, because a lot of opportunities and avenues are available on those hilly regions. Now, on contrary, each mirror needs an individual dual axis control, while the PTC system can share it to a large mirror array. Now, this increases the operational problem related to the calibration and adjustment of mirrors in a large spectrum or a large scale. Now, there are some existing solar tower plants. This includes 2.75 megawatt of solar tower power plant. This has been installed by ACME in Bikaner, Rajasthan. The turbine pressure and the temperature are 60 bar at 440 degrees Celsius. World's largest heliostat with an area of 150 square meter has been installed at Gurgaon with an aim to set up 1 megawatt or thermal power, and sometimes referred as 1 MWTH, CSP Central Tower Plant facility in India. The main objective of this power plant is to development of optimized design of the heliostat field, volumetric air receiver, and thermal storage, and three major component of a concentrated solar power, that is CSP, the central receiver plant. Another objective is to develop or development of local sources for all the key components of the plant, with a focus on lowering costs, which will make the technology competitive with other forms of energy. Now, another thing is that which we would like to discuss is the parabolic dish or PD technology. The parabolic dish system is parabolic disc type geometry of mirrors mounted over a reflector dish to focus the solar radiation at the receiver. Now, here you see that the receiver engine and all these things are addressed to the receiver engine. The basic component of parabolic dish system, this consists of a solar reflector, this one, a receiver, and mounting structure. Now, this solar reflector is supported over the dual axis solar tracking system, which allows the continuous tracking of the sun radiation, orienting the disk accordingly. Now, the focused sun rays from the reflector is then get concentrated towards the central receiver, fixed at the focus of the parabolic dish. So, focusing is important. Now, this receiver is attached with a heat engine containing thin tubes filled with various gases. Now, these gases can be helium, hydrogen, nitrogen, or air. It depends on the, or it is based on according to the engine properties. Now, the associated heat engine, it usually work on Stirling or Brayton cycle. The sun rays collecting at the receiver, here you can see, these can heat the gas up to 750 to 1000 degrees Celsius. The hot gases inside the heat engine, they they are having the tendency to expand, driving the piston inside the cylinder. The piston then rotates the crankshaft, connecting with it and starting the generation of electricity. So it's a very simple and very common phenomena. Now, this process has a similar type of a principle with as we are observing in internal combustion engine. Now, as the combustion process occur outside the piston cylinder geometry, the parabolic dish system can also be referred as an external combustion engine. The parabolic dish system is majorly used for the electricity generation through the Stirling engine. Now, people have carried out various studies in this particular approach, and a few studies reported that the solar to electrical energy conversion efficiency of Stirling engines, it can go up to 30%, which is you can say the comparatively higher than other solar assisted technologies. But once these parabolic dish offers various advantages, there are so many limitations of parabolic dish that is also attributed to the system. Now, a parabolic dish is a type of solar concentrator that follows the sun and generates an image of it at the focal point. While point concentrators are available, there is a financial and technological gap that must be bridged. Now, there may be attributed to the deviation in geometry, and the deviation in geometry have the potential to drastically reduce the efficiency of dish system. So, in view of this, the design precision and flexibility or utmost precision is extremely important and it is required. There are existing PD systems in India. Now, Stirling engine for net 1.5 kilowatt electricity output has been designed at Indian Institute of Technology, Bombay. Now, it was observed that the engine ran for 11 seconds with electrical heater furnace as the heat source. The maximum speed observed was about 1000 rpm during the trial run, and they have achieved the efficiency between 30 to 35%. Now, another solar Stirling engine has been developed by ONGC in collaboration with Infinia Company, USA, and installed at NIC for the performance evaluation test under the Indian climatic condition. Now, this system has two axis tracking, and that is it tracks the sun according to the time of the day and also according to the time of the year. As a result, it always faces towards the sun and concentrates all the direct solar radiation falling on that particular aperture. The Stirling engine at the receiver point of the dish concentrator is a helium gas engine with free piston. Now, we have discussed a lot of about the solar energy, and you see that whenever we are talking about the solar energy, the integral component of these solar energy was the heat transfer fluid. Now, heat transfer fluid, as we previously discussed, they offer a very good spectrum in all chemical engineering applications, and especially when we look for heat transfer media, then definitely all these heat transfer fluids, they came into existence. One of the widely applicable heat transfer media or fluid is water, apart from the air. Now, water offers a wide spectrum with respect to the abundance, with respect to the ease in use, with respect to the neutrality, etc. But it has several limitations that you cannot go beyond certain level. So, we have to look for the various other heat transfer media or the fluid, keeping in view of the variety in the chemical engineering approach. And simultaneously, the refrigerant also plays a very vital role, and they are also clubbed with the heat transfer media. So these can be distinguished because we are having n number of processes simultaneously, we are having n number of heat transfer media. Now, when we are saying that we are having n number of heat transfer media, then we need to have some distinguishment. So one distinguishment can be based on to their range of application. Now these heat transfer media or the refrigerant, they are capable of operation from say minus 100 degrees Celsius to say up to 250 degrees Celsius, and sometimes minus 50 degrees Celsius to say up to 700 degrees Celsius. Now, a heat transfer media or a medium in the most general sense, this may be present in the solid, maybe in the liquid or in the form of a vapor phase. Like we used the gaseous heat transfer media in the parabolic dish type of a system. So, it can be used to store the heat in a reversible form. It can be circulated within the installation, sometimes pipes, sometimes some other storage media like this. So the phenomena is quite simple. It absorbs heat, discharge heats, and again go back to its previous condition. Now, when we talk about the multi-phase substances, so with these multi-phase substances, a change of phase will occur during the heat exchange with the surrounding, and considerable amount of enthalpy being exchanged. So, when we studied the different type of CSP technologies, so it can be observed that most common and influential component in these system are heat transfer fluid, as evident when discussed so many processes, and you can see sometimes the liquid, sometimes the gaseous form they are being used. So these heat transfer fluid circulates throughout the tube to transfer the thermal energy, and therefore is required to in the much higher amount. So it is always preferred to minimize their uses and select the cheaper fluid. We may have a debatable thing on this cheaper fluid. Sometimes the cheaper fluid may have a corrosive effect. So while adopting this economical approach, one must look different parameters. Maybe which kind of a fluid be used. It should be non-corrosive, it should be non-reactive, it can recirculate easily, it can discharge the heat to the port as quickly as possible. So all these things must be addressed. So it also help these heat transfer fluid, they helps in the energy storage by keeping the hot heat transfer fluid in an insulated chamber, which can help in the continuous power generation. Now there is a broad spectrum of selection criteria. The question arises that we are having wide galaxy of heat transfer fluid, then how we can select the appropriate heat transfer fluid. Now one criteria that it should have a lower melting and a higher boiling point. It should provide low vapor pressure, maybe sometimes less than 1 atmosphere at higher temperature. It should be thermally stable and pose minimum corrosion to the storage tank and tubes where it will be circulated. It should have a low viscosity and higher thermal conductivity and higher heat capacity. It is the foremost requirement, higher thermal conductivity and high level of heat capacity. And it should be cheaper and regionally available, so that when you are using, it must not pose any kind of availability issues. Now, these heat transfer fluid broadly can be classified into 6 different categories. As we discussed, that air and water, they are most abundantly available heat transfer fluid. So, one category is air and gas, second may be the water or steam. Then we are having various thermal oils. Sometimes the synthetic organic fluids or various organic fluids, they can be act as a heat transfer fluid. Molten salts, they are a very good candidate of heat transfer fluid. Liquid metals, they are having wide range of heat transfer temperature difference. Now, among them, the molten salts are industrially widely accepted as a high temperature heat transfer fluid, providing high heat capacities. They are having highly thermal conductive in nature. They possess the low vapor pressure and less corrosive properties. Another important heat transfer fluid, they are the liquid metals capable of providing similar operational characteristics which we discussed for the molten salts. Other competitive and cheaper alternatives, they are including some organic and thermal oils, and organic sometimes they are the synthetic organic segments. We have already discussed various things related to the heat transfer fluids in the CSP section. Usually, the higher efficiency is obtained at higher temperature operation. Now, there are, you can say, the less options available for heat transfer fluid at a temperature up to say 900 degrees Celsius, which includes molten salt, metal, gases, sometimes like carbon dioxide, etc. But when we go for a higher temperature, the issue pertaining to the corrosion, it also prevails. So, all these things while designing, while selecting, while developing any kind of system must be addressed. So, let us discuss one by one, that is air and other gases, that is the first category. Now, air is not you can say much widely commercially acceptable, but highly studied heat transfer fluid. The reason is that it is available in abundance. It is available virtually at free of cost. This air can be heated up to 700 degrees Celsius at atmospheric pressure, which can be further used to produce superheated steam. Now, it can considered as a cheapest, as I told you, cheapest because it is available in abundance and sufficiently available heat transfer fluid. This is having the lower viscosity, that is 3 into 10 to the power minus 5 pascals as compared to the molten salt and liquid metal, and approximately 65 and 10 times compared to the molten salt and liquid metal respectively. Now, this low viscosity enhances the flow characteristics inside the tube, which increases the rate of heat transfer. But so in one way it is economical, but because of the low thermal conductivity of air, this is the inherent disadvantage. So, the major disadvantage associated with the air is that it possesses very low thermal conductivity. The corrosion characteristics for air also depends on the type of impurities present in the steel using piping. So, sometimes metal like chromium, aluminum, this can help to reduce the corrosion by forming a protective oxide layer over the steel surface. There are certain noble metals above steel like copper, nickel, they do not pose any corrosion changes. High carbon steel is also favorable and corrosion resistive at temperature operations nearly at 700 degrees Celsius. Apart from air, helium and supercritical carbon dioxide, they has also been studied as a heat transfer fluid. Helium is already in use for high temperature nuclear reactors, and it can be affordably obtained from a natural gas processing. Helium can also be used in high temperature CSP just like air, but it poses a very low heat capacity and thermal conductivity. Now, these are several limitations which need to be addressed. To overcome these limitations, one can or entire operation can be operated at high velocity and high pressure. Supercritical carbon dioxide, on the other hand, it can achieve better efficiency at lower temperature CSP compared to the steam and helium. So, as it requires a high pressure operation, uses is limited to CSP like power towers. Supercritical carbon dioxide or CO2 as a heat transfer fluid is a topic of high research interest nowadays. The people are working on over it. Several research works are also going on in this field, and it can be considered as a future heat transfer fluid, at least for the power towers based on CSP. Now, in this particular lecture, we had discussed about the different heat transfer fluids. We had a discussion about the classification of these heat transfer fluids, briefly about that what are the desirables of these heat transfer fluids, what should be the selection criteria of these heat transfer media. Now, if you wish to have a further study, we have enlisted 4 different references. You can have a look of all those references if needed. Thank you very much.